ready to do the other settings similar to the previous one of using snap hex mesh, because the following operations will be the same. So the previous of use snap hex mesh, and now use the third-party meshing software of Salmon to create mesh regions. So we have done that, and we know we can do that previously, all of them in a text file editor, or natively if you are a programming person. So if you programmed before, you can use the VS Code. So add this OpenFOAM path. If I just directly type code dot, that will open the VS Code environment. If you have installed this software package. Now what I'm interested in now, so it load all these three folders, the three main folders: 0, constant, and system. So I'm currently interested in the constant, and constant we have the air and water and polymesh. Now I'm interested in the regional polymesh and the boundaries. So what I'm going to check now is the constant, different regions, and polymesh boundary files, because by default all these boundaries, I mean the geometric boundaries, have the patch or mapped walls unless it is the interface. We know the air to domain 0 is actually, it's not a patch, right? It's all the external, so I name it as wall, right? And now go to the water, and polymesh also have the boundary, and the wall of domain 0 is also wall. And if you want to check the interface of the air to water or water to air, so I will open this air to water, and this is water to air. It also, the number of faces for each is 6,454. That all make sure the interfaces have the same number of faces, and also the nearby patch faces is correctly defined. So that is quicker than the previous setting of using the snap hex mesh, because modeling or the processing mesh has been mostly corrected. We only need to correct the wall for the external faces. So that's for the constant, and for the others we follow the same procedure of defining the region properties, the gravity, and the thermal properties and turbulence for each region, right? So we'll copy this from our previous setting. So our previous setting, I have got this gravity and the region properties. I directly copy to my constant folder here, so no problem. And because the region properties, we only have two regions as water and air in the fluid, and also the gravity is along the, but I can actually use the VS Code if you have that. So the constant, now I have got the gravity, so the gravity is along the y direction, right? So minus 9.81 is y direction. Okay, the region properties also has been defined. And now we go to the copy of thermal physical properties and turbulence properties for different regions. So make sure this is my previous setting. I go to the air and copy the air thermal properties and thermal physical properties here for air, and then go to water, and I will copy the water from the previous setting. So if you haven't read the previous or watched the previous videos, please do that, and I have a clear explanation of doing how to set them up actually in the very first CHT conjugate heat transfer from scratch. Okay, that's our main settings for the constant if I go to the constant again, I will see the thermophysical properties here. That is for the air and that for the water. So different settings, if you can see, it's different settings for the water and air, right? So different physical properties. Turbulence property, we all think it's laminar, so still laminar flow. And now let's go to the final step of covering all the boundary definitions. If you still remember, I currently have all the patches, all the boundaries defined with the same name of previous setting. That made me quite easy. So all the previous settings for the air and water still applies here. I just directly copy them to the corresponding folder for the air, for example, and water. So I just need to find the water. For here, water, that is water boundaries. So 4 boundaries of the pressure, the absolute pressure minus the height, so the static fluid pressure, and the thermal and velocity. So if you want to check, now I have the 0 folder and I have all the boundaries, right? So the air inlet, air outlet. Oh, I need to correct here. So now I don't have the air misfits, right? So I only have the air to domain 0. So I need just to make sure all this air misfits is not used, just air to domain 0. And for the every that's only the external wall currently, so air to domain 0 and air to domain 0 here as well. That is for the air side, right? For the water side, I also need to make the change because I also have the water misfits. Now I don't have the misfits anyway because I use the third-party software of doing that help prevent all these phases. So I just correct all of this by deleting the irrelevant phases. That will give me all this correctly defined, right? So that is all this defined, and we go here, and now we are ready to run the simulation. For running the simulation, we actually need a final check of the system folder because we haven't got much definitions in the system folder, only the control dict, and these two are actually directly copied. We haven't got any definitions yet for the air and water, so that means I need to go back to my previous method of using snap hex mesh. I will copy the FV schemes for both water and air. So I go to here, that's my current folder system. I will just paste and overwrite the system definition for the FV scheme and FV solutions because the previous one is only about the meshing operation. So that's not for the solving. So that means we have correctly. So the DDT scheme is steady state, and we have all these definitions defined, and also have the especially for the thermal simulations. That's good. And also I have the final check of the control dict. Yeah, it's CHT multi-region simple form. So because now I use the VS Code, I think it's ready to allow me to run the simulation. I can run it here. or I can run it in the VS Code. So I'll run the CHT multi-region simple form here. And now the program started to run the solver, and I will pause now and see how it works after the running.